Imagine, you're standing on the bridge of a starship. A vast panoramic window reveals the velvet black of space, sprinkled with the diamond dust of distant stars. Your destination? A planet orbiting Proxima Centauri, the nearest star to our own sun. It's a journey of over 4 light-years. With today's technology, a trip like that would take tens of thousands of years, a multi-generational voyage into the unknown. But on your ship, the journey takes mere days, perhaps even hours. The captain gives the command, and the stars outside don't streak past. They warp, they bend, space itself seeming to fold around you as you leap across the cosmic ocean. This isn't just science fiction, it's a dream rooted in one of the most profound questions we can ask. Can we ever break the speed of light? This grand vision of interstellar travel has captivated us for generations. We are a species of explorers, driven by an insatiable curiosity to see what lies beyond the next hill, the next ocean, the next world. The cosmos is the ultimate ocean, and its shores are galaxies untold. To reach them, to truly become a spacefaring civilization, we must confront the greatest barrier we know of, the universal speed limit. It's a law not written in any book on Earth but etched into the very fabric of space-time itself. But what if we could find a loophole? What if the rules, as we understand them, are incomplete? So, come with me. Let's embark on a journey of the mind. Let's explore the science, the theories, and the breathtaking implications of a future where humanity slips the surly bonds of light speed. Before we can talk about breaking a speed limit, we need to understand the limit itself. What is light? It's the familiar stuff that streams from our sun. It illuminates our world and lets us see. It's the glow from our screens, the twinkle of a distant star. In physics, light is an electromagnetic wave, a traveling disturbance in invisible electric and magnetic fields. It's also a particle, a tiny packet of energy called a photon. That dual wave particle nature shows light is special. It is the messenger of the cosmos, carrying information to our telescopes. Now let's talk about its speed. In a perfect vacuum, light travels at 299,792,458 meters per second. Call it 300,000 kilometers per second, or about 186,000 miles per second. Fast enough to circle the Earth more than 7 times in a single second. A beam of light can travel from the moon to Earth in a little over a second. The light from our sun takes about 8 minutes to reach us. This isn't random. It's a fundamental constant we call CHC, is the maximum speed for any information or cause and effect. When a distant star explodes as a supernova, we cannot know until its light reaches us. The gravitational waves from that explosion also travel at c. Everything without mass travels at this ultimate speed. Photons, gluons. It is the universe's top gear. Nothing we know can go faster. This speed defines our cosmic horizon. The universe is about 13.8 billion years old, so the farthest light we can see has been traveling 13.8 billion years. The speed of light is a celestial time machine. Andromeda is 2.5 million light-years away, so we see it 2.5 million years in the past. The speed of light is our ultimate ruler and our ultimate clock, the benchmark for all motion. So, why can't we just build a really powerful rocket and push it past the speed of light? The answer lies in the revolutionary ideas of a young patent clerk named Albert Einstein. In 1905, he published his theory of special relativity, and with it, he rewrote our understanding of space, time, motion. One of its most famous conclusions is that the speed of light in a vacuum is the same for all observers, no matter how fast they are moving. This simple-sounding idea has profound and bizarre consequences. It means that our common-sense notions of speed, which work so well for cars, baseballs, completely break down as you approach c. Here's the cosmic catch. According to Einstein, as an object with mass, like a spaceship, you, me, accelerates and gets closer to the speed of light, its mass begins to increase. Not because it's picking up more atoms, but because energy and mass are two sides of the same coin, as described by the famous equation E equals mc squared. The kinetic energy you pour into the object to make it go faster starts converting into mass. This isn't just a theoretical quirk. Particle accelerators like the Large Hadron Collider at CERN have to account for this effect every single day. They accelerate tiny particles to 99.9999999% of the speed of light, and those particles become incredibly massive. Imagine you're pushing a car. At first it's easy. But as you push it faster and faster, approaching the speed of light, the car feels heavier and heavier. Each push gives you less and less acceleration. As you get infinitesimally close to light speed, the car's mass approaches infinity. To push an infinitely massive object, you would need an infinite amount of energy. And since there isn't an infinite amount of energy in the universe, you can never quite get there. The speed of light isn't just a speed limit, it's an asymptotic barrier. Einstein's theory also revealed that space and time are not separate and absolute but are interwoven into a single, four-dimensional fabric, space-time. So while you can't break the speed limit, you can use it to travel into the future. But going faster, that requires a different way of thinking. If you can't move through space faster than light, what if you could move space itself? This is the brilliantly clever idea behind the Alcubierre warp drive, a theoretical concept proposed by physicist Miguel Alcubierre in 1994. It's the closest thing real-world physics has to the warp drives of science fiction. The idea doesn't break Einstein's law, it finds a loophole. The rule is that nothing can travel locally through space-time faster than light. But Einstein's later theory of general relativity shows that space-time itself is flexible. It can be bent, stretched, warped by mass and energy. The Alcubierre drive proposes to use this flexibility to its advantage. Imagine your starship is sitting on a cosmic surfboard. The drive would work by creating a warp bubble of space-time around the ship. In front of the ship, space-time would be compressed, effectively pulling your destination closer to you. Behind the ship, space-time would be expanded, pushing your starting point farther away. The ship itself wouldn't be moving through space in the traditional sense. It would be at rest inside this bubble of calm, normal space-time. It is the bubble itself that moves, carrying the ship along with it. From the perspective of someone inside the bubble, nothing is moving at faster than light speeds. But the bubble's journey across the cosmos could be accomplished faster than a beam of light could make the same trip. This is like standing on a rug and pulling the far end of the rug toward you. You haven't moved on the rug, but your position in the room has changed. In this analogy, you are the starship and the rug is space-time. Because the ship inside the bubble is technically stationary with respect to its local environment, it doesn't experience any of the bizarre relativistic effects like time dilation or infinite mass increase. The crew would experience no sense of acceleration at all. They could sip their coffee while crossing the galaxy in a week, arriving at their destination with their clocks perfectly synchronized with where they left. Of course, there is a very big catch. To create this space-time distortion, you would need a truly exotic form of matter. Matter with negative mass, or more precisely, a negative energy density. We've never observed such a thing. Another tantalizing possibility for faster-than-light travel: Einstein-Rosen bridge, more popularly known as a wormhole. If you think of space-time as a giant two-dimensional sheet of paper, the fastest way to get from one point to another is a straight line. But imagine folding that paper, bringing the 2 points right next to each other, then poking a hole through it. You wouldn't have crossed the paper at all. You'd have taken a shortcut through a higher dimension. That's really the essence of a wormhole. It's a theoretical tunnel through space-time connecting two very distant points in the universe, or even two different universes entirely. Imagine you want to travel from your living room to your kitchen. Normally you'd walk down the hallway, but with a wormhole you could open a portal on your living room wall that leads directly to a portal on your kitchen wall. You'd step through and be there instantly. A cosmic wormhole would do the same thing on a galactic scale. One mouth of the wormhole could be here in our solar system, while the other could be millions of light years away in the Andromeda galaxy. By stepping through, you could traverse an immense cosmic distance in a matter of minutes, effectively traveling much faster than light could have across the intervening space. Like the warp drive, the wormhole is a way to cheat the cosmic speed limit without actually breaking it. This concept has fired the imagination of storytellers for decades, presenting a vision of a galactic subway system where different worlds are just a step away. Imagine a network of stable wormholes connecting star systems, making interstellar trade, exploration, and colonization as routine as taking a train to the next city. But here again, we run into the buzzkill of theoretical physics. Just like warp drives, traversable wormholes would require vast amounts of that same exotic negative energy matter to prop them open. Without it, the intense gravity within the wormhole's throat would cause it to collapse into a singularity the instant it formed, or the instant anything tried to pass through it. We've journeyed from the nature of light to the mind of Einstein and to the frontiers of theoretical physics, warp drives and wormholes. These are really big ideas. They stretch the mind and spark the imagination. They are the essence of scientific curiosity, looking at the universe and asking, what if? The journey to understand the universe is collective. It's built on shared knowledge and shared passion. If this journey is making you wonder, hit that like button. Want to miss nothing? Subscribe and ring the notification bell. If we could travel faster than light, one of the most mind-bending consequences would involve our relationship with time itself. Many physicists believe that FTL travel is inextricably linked with time travel into the past. This is because special relativity treats space and time as a unified whole. One observer sees a journey through space, another observer at a different velocity could see that journey arriving before it even started. This leads to the famous problem of causality. Cause must precede effect. Imagine a spaceship that can travel FTL. Travel to a star 10 light-years away, turn around and return to Earth, all in a single Earth week. You'd arrive nearly 20 years before the light from your departure reached that star. From some frames, your return looks like backward time travel. This opens a Pandora's box of paradoxes. What if you prevented your parents from meeting? That's the grandfather paradox. Some theories offer solutions. Chronology protection conjecture, a timeline firewall, or changing the past spawns a parallel universe. Set aside paradoxes and consider another effect, looking into the past with perfect clarity. Instantly travel 65 million light-years away. Point a super-powerful telescope back at Earth. You wouldn't see Earth today. You'd see the light that left Earth 65 million years ago. You could witness the asteroid impact that led to the extinction of the dinosaurs, not as a simulation, but as it actually happened. We could become cosmic historians watching the birth of our planet, watching star formation, watching the great events of cosmic history. The past would become an open book. The ability to travel between stars faster than light would fundamentally rewrite the human story. For our entire existence, we have been a species confined to a single fragile planet. The distances between stars are so vast, they've acted as an insurmountable wall, locking us inside the solar system. Breaking the light barrier would be like a landlocked species suddenly learning how to swim and breathe water. A boundless cosmic ocean would open up before us. Proxima Centauri, our nearest neighbor from a 75,000-year journey to a weekend trip, the galaxy would become our backyard. This would trigger a new age of exploration dwarfing the voyages of Columbus and Magellan. We could send probes, then people, to thousands of exoplanets. We could search for habitable worlds, Earth 2.0's quote comma, where humanity could establish new branches of civilization. This wouldn't just be a safety measure to ensure our survival. It would fulfill our exploratory drive. We would no longer be Earthlings, we would be citizens of the Milky Way. Think of the scientific discoveries that would follow. Visit worlds with different chemistries, different biologies, different geologies. Study neutron stars and black holes up close, testing gravity in extreme environments. And of course, there is the biggest question of all, are we alone? Not just listening for radio signals, but actively going out and looking. Visit planets with signs of life in their atmospheres, see what lives there or who lives there. First contact becomes a statistical likelihood. The social and cultural impact would be profound. New colonies would develop their own cultures, their own societies, their own identities. A vast interstellar economy could emerge from resources and exchange knowledge. Humanity would diversify yet stay connected by star lanes of FTL travel. The beginning of a new human saga, not on continents but across the spiral arms. Right now we are like infants in a cradle. Our world is everything we know. The twinkling lights on the ceiling of our nursery are beautiful but unreachable curiosities. Learning to break the light barrier would be like taking our first steps out of that cradle and into the wider house. It would transform our perspective forever. The universe would no longer be something we just look at. It would be a place we can go. Our cosmic loneliness would be replaced by a sense of boundless opportunity. This transformation would force us to confront who we are and what we want to become. And interstellar humanity would need to be united in purpose, if not in governance. The challenges of colonizing new worlds and potentially meeting other intelligent species would require cooperation and wisdom we have yet to achieve on Earth. The technology to bend space-time is a technology of immense power. It could be used to connect and enlighten, or to become a weapon of unimaginable destruction. Our technological maturity would have to be matched by ethical maturity. Whether we achieve FTL through warp drives, wormholes, or some other method we can't yet conceive of, the pursuit itself is invaluable. It pushes the boundaries of knowledge, forces the biggest questions, and inspires us to dream. The math and physics from that chase could spark breakthroughs in energy, computing, and our understanding of reality. The journey is as important as the destination. The dream of the starship propels today's science. So, the next time you look up at the night sky, at the countless stars scattered across the darkness, don't just see them as distant points of light. See them as destinations, see them as possible futures. The universe isn't shouting no, it's whispering the rules. Now see if you're clever enough to find a way around them. Our future, one way or another, is out there, among the stars.